Hello, welcome to AccuStrata's online demonstration. Today we are going to demonstrate to you the operation of our real-time optical monitoring system and the manufacturing of amorphous silicon thin film solar panel. The purpose of the system is to monitor the film parameters during the film growth, compare them with some target parameters, and generate a message to the operator proposing necessary corrective actions in case of drift of these parameters from their targeted values. Our system can also be designed to correct the process parameters automatically in real time, so that the panel achieves higher efficiency without human involvement. The typical amorphous silicon thin film solar panel manufacturing line is a vacuum chamber of 3 separate compartments. In this configuration, the panel enters the first deposition equipment with already pre-deposited transparent conductive oxide, a process which is not illustrated on this slide. On the left side is the first chamber compartment, which is used to deposit the so-called P amorphous silicon layer. After the P layer is deposited, the panel enters the next chamber, where the most important absorber layer, the I amorphous silicon layer, is deposited. Last, the N amorphous silicon layer is deposited, ending the formation of the photovoltaic PIN junction. In this example, the panel is stationary during the deposition of the films. Inside each of the individual deposition compartments, we are installing our patented fiber optic arrays, which are able to monitor the process of film growth at different positions on the substrate. Our optical monitoring system comprises of these fiber optic arrays, the hardware module, and our software program with intelligent predictive capabilities. The history of each manufactured panel at all 3 compartments is recorded into a database. The histories of the best panels, such as panels with best efficiency, are processed by our software to deduct theoretical response surface models, which can be later used in order to change the process conditions for each panel and achieve the best performance. As each panel is undergoing deposition, our software retrieves from the database all similar histories and predicts what the final quality of the panel will be ahead of time. Once the suitable response surface model is identified, it is used to create an adaptive correction, which will adjust the process in advance in order for the panel to achieve the same best quality as the chosen model. On this picture, we are showing how our prototype system was installed in a real manufacturing line. We have installed 2 optical monitoring arrays, one in the chamber where the P layer is deposited and one where the I layer is deposited. The optical monitoring system is installed using this fiber optic vacuum sealed feed-through. There are 2 fiber optic sensors installed inside each of the chambers. They are not visible. One is located on the bottom of the chamber and the other one on the upper side of the chamber, and they monitor 2 different areas of the panel, a bottom area and an upper area. Our hardware modules that supply the illumination light to the sensors and analyze the reflected light are located on the table in front of the equipment together with our computer and the operation software. We will limit this demonstration to the operation of our system only in the I chamber, where the main absorber is deposited. As the deposition takes place, we are acquiring real-time data for the specular and diffuse reflectance of the panel at different wavelengths. Here we are displaying the signal at one specific wavelength for one of the optical sensors in the I chamber. The blue one is the acquired signal from the sensor, and the red curve is our theoretical fitting to this monitored curve. Our software calculates important physical parameters for the film, which are displayed on the right side of the screen. The first parameter is the thickness of the film versus the time of deposition. From this curve, we calculate the deposition rate of the film, which is about 6.5 angstroms per second. The second parameter that is displayed on the screen is the refractive index of the film, which in this case drops during the deposition. The refractive index at this specific wavelength drops by about 10 to 15% from its initial value during the deposition of the film. The extinction coefficient of the film here is increasing during the deposition, indicating some physical changes in the film material. These changes can be associated with the material microstructure, presence of contamination, change in the material band gap, or others. The next parameter is the material band gap, which changes from 1.75 electron volts to about 1.5 electron volts. On the next screen, the differential signal between the two sensors is displayed. Here the red curve shows the first sensor, and the blue the second sensor, and the difference between them is a witness of non-uniformity, which is taking place not only in the thickness of the film, but mainly in its optical parameters. It is clear that the refractive indexes in the two areas of the panel are different. On the right side, we see the thickness of the film as displayed by the two sensors, and the differential signal between them is the measure of the film non-uniformity, which is about 15 nanometers. Having this information in real time as the film is deposited allows us to change some process parameters in order to compensate for the difference in the film thickness at the two panel areas and return the panel to its intended quality. For additional information, please contact us at our website, www.AccuStrata.com. Thank you very much, and we look forward to hearing from you.